I'm presenting a problem about semi-supervised learning. We have a dataset 1000 samples, but only 100 are labeled. We'll use scikit-learn's LABELPROPAGATION and LABELSPREADING algorithms to find the best approach. Pretty cool, right? Here's the main question. I want you to identify which statements accurately describe the LABELPROPAGATION and LABELSPREADING algorithms in a semi-supervised learning setting. It's like a multiple-choice quiz to test your understanding. Let's look at statement A. LABELPROPAGATION always finds a solution. It converges. LABELSPREADING, on the other hand, might not, depending on its settings. It's a bit more unpredictable. Statement B focuses on a key difference. LABELSPREADING uses a mathematical function called a kernel to weigh how much labeled data points influence their neighbors. LABELPROPAGATION keeps things simple and doesn't do this. Statement C points out a shared weakness. Both algorithms can be sensitive to errors in the initially labeled data. If I start with bad labels, I'll end up propagating those errors to other data points. That's something to keep in mind. This statement is tricky. While generally more labeled data helps, it's not a guarantee. The quality of the additional labels is also very important. Adding more bad labels might actually make things worse. This tells us we're dealing with a semi-supervised learning problem. I have a dataset with 1000 data points, but only 100 have labels. The rest are unlabeled. This is a common scenario where label propagation algorithms like label propagation and label spreading shine. We'll use these 100 labeled samples to help us predict the labels of the remaining 900. It's like having a few puzzle pieces, and I need to figure out the entire picture. Label propagation, in its basic form, is guaranteed to converge. I will always find a stable solution after a certain number of iterations. This means the algorithm will stop changing its predictions eventually. It's like a ball rolling downhill, it will eventually stop at the bottom. It's a reliable method for label propagation. Label spreading is different. It's kernel-based, meaning it uses a kernel function, like the radial basis function or RBF, to weigh the influence of each labeled sample on its neighbors. I use the kernel to measure the similarity between data points. Points closer together have a stronger influence on each other than points farther apart. Think of it as a weighted vote. Closer, more similar neighbors have a louder voice in determining the label of an unlabeled point. I'm focusing on two. Scikit-learn. Algorithms for semi-supervised learning. Label propagation. And label spreading. These algorithms cleverly use a small set of labeled data points to predict the labels of the rest of the data. Think of it like this. You have a few puzzle pieces with colors, and these algorithms help figure out the colors of the remaining pieces based on how the pieces fit together. I'll be evaluating how well LABELPROPAGATION and LABELSPREADING work using a dataset with 1000 samples. Only 100 are labeled. This mimics a common real-world situation where labeled data is scarce. The goal is to find the best algorithm for this semi-supervised learning scenario. Label propagation always finds a solution, it converges, but label spreading might not, depending on how it's set up. It's like a race. Label propagation always finishes, while label spreading might sometimes get stuck. Label spreading uses a kernel, a function that measures how similar data points are. Think of it as weights determining how much influence one data point has on another. Label propagation is simpler, it doesn't use these weights. Label spreading is more sophisticated. Both algorithms can be messed up by bad labels. If some initial labels are wrong, both algorithms will propagate those errors, leading to inaccurate predictions. That's like building a house on a bad foundation. Adding more labeled data usually helps, but it's not guaranteed to always improve performance. The quality of these extra labels matters. If the new labels are inaccurate, this could actually hurt the performance. We have a dataset with 1000 data points, but only 100 of them have their labels, the correct answers, specified. The algorithms need to predict the labels for the remaining 900 points. This is our real-world problem that highlights scarcity of labeled data. This is one of the two algorithms I am evaluating. This is the other algorithm that I'm comparing to label propagation. We're diving into a type of machine learning called semi-supervised learning. Imagine you have a huge pile of data, but only a tiny part is labeled, like having 1,000 pictures but only knowing the names of 100. Label propagation and label spreading are like clever detectives. They use what they do know to figure out the labels for the rest. We'll be using them to see how well they solve this mystery. It's like a puzzle, but with algorithms. I have a dataset with 1,000 samples and only 100 are labeled. The goal is to understand how label propagation and label spreading behave in this situation. Let's solve the mystery. I'm testing your knowledge of these two algorithms. Which of the statements below are true about how label propagation and label spreading work and behave? Think carefully about how each algorithm works to find the right answer. This algorithm iteratively propagates labels. Think of it as a ripple effect. I start with a few labeled points, and the label spreads to nearby unlabeled points based on how connected they are. It always reaches a stable solution, converges. Similar to label propagation, but I uses a kernel function to weigh the influence of labeled points on their neighbors. This is like assigning weights to the connections. Some connections are stronger than others. This weighting can affect whether or not it reaches a stable solution. It might not always converge. Label propagation iteratively spreads labels. Because of this iterative nature, it is guaranteed to converge. It will always find a stable solution. Label spreading uses a kernel to weigh the importance of connections between points. Because of the kernel's influence, convergence is not guaranteed. It might not always find a stable solution. We're evaluating how well label propagation and label spreading work in a semi-supervised learning situation, where we only have labels for a small part of our data. We'll assess several claims about these algorithms' behavior. This helps us understand their strengths and weaknesses. I observed that label propagation always reaches a stable solution because it's a straightforward iterative process. However, label spreading, with its use of a kernel, can sometimes fail to converge depending on the kernel function and the data characteristics. I found that label spreading cleverly uses a kernel function, think of it as a weighting system, to decide how much influence labeled data points have on their unlabeled neighbors. This allows it to consider the similarity between points. Label propagation, on the other hand, doesn't use this sophisticated weighting. I determined that both algorithms are vulnerable to errors in the initial labels. Because they spread information based on these initial labels, inaccurate labels contaminate the results, propagating those errors. Think of it like a game of telephone. A small error at the start becomes amplified. I discovered this statement to be false. While it's generally true that having more labeled data helps, it's not guaranteed. If the new labeled data is poor quality or doesn't represent the rest of the data well, it can actually hurt the performance. It's not just the quantity but also the quality of data that matters. I'm tackling a problem in semi-supervised learning, which means I have a dataset with many unlabeled data points and only a few labeled ones. I'm using two algorithms, labelpropagation and labelspreading, to predict labels for the unlabeled data points. This is similar to trying to guess the colors of unseen marbles in a bag, based on the colors of only a few that I can see. I'm evaluating several statements comparing labelpropagation and labelspreading. I need to determine which statements are correct. Let's dive into statement A. Labelpropagation always finds a solution, like a determined hiker always reaching the summit. Labelspreading, however, might get lost sometimes and not find a solution, depending on the details of how it's set up. Moving on to statement B. Labelspreading uses a mathematical function called a kernel to decide how strongly one data point influences another. Imagine it as a magnifying glass. Some data points' influence is magnified more than others. Labelpropagation doesn't have this feature. All data points' influence is treated equally. Let's tackle statement C. Both algorithms are like gossips, they spread information quickly. If the initial information, labels, is wrong, noisy, then the propagated information will also be incorrect. And finally, statement D. While adding more labeled data often helps, it's not a guarantee. It's like having more clues to solve a puzzle. More clues are usually better, but not always. The additional data might not always be helpful and could even hurt performance. I'm working with a dataset of 1,000 samples, but I only know the labels of 100 of them. This is my semi-supervised learning setup. I'm comparing these algorithms to see which is better at handling situations with limited labeled data. Statement A is true. I confirmed this with my understanding of each algorithm. Statement B is also true. I analyzed how kernels function in label spreading and their absence in label propagation. Statement C holds true. The sensitivity of both algorithms to noisy labels was also verified. Statement D is false. It is not always guaranteed that additional labeled data will improve model performance. I'm presenting you with a problem about semi-supervised learning, using SCIKITLEARN, SLABELPROPAGATION and LABELSPREADING. We have a dataset of 1,000 samples, but only 100 are labeled. We'll explore different ways to use label propagation to find the best strategy. This is the dataset. I'm working with 1,000 data points. But, only 100 of these have their class labels assigned, which is a common scenario in semi-supervised learning. This creates a challenge because I don't have labels for most of my data. This is an algorithm. It's like a game of telephone. I start with a few labeled samples and I iteratively spread their labels to unlabeled samples based on how close they are to each other. The closer they are, the more likely they share the same label. Think of it as information spreading through a network. Similar to label propagation, but with a twist. This algorithm uses a kernel function, kind of like a weighting system. This means that the influence of labeled samples on their neighbors isn't uniform. Some neighbors have more weight than others depending on their distance, similarity, or relationship according to the kernel. I use this to better manage the label propagation process. Both algorithms, LABELPROPAGATION and LABELSPREADING, are sensitive to noisy labels. If some of my initially labeled samples are wrong, the algorithms might propagate these errors throughout the dataset, leading to inaccurate predictions. LABELPROPAGATION always finds a solution. However, LABELSPREADING might not always reach a stable solution, depending on factors like kernel choice and parameters. LABELSPREADING uses a kernel function, a weighting system, to give different influences of labeled samples on unlabeled samples. LABELPROPAGATION doesn't have this kernel-based weighting. This is not guaranteed. Adding more labeled data generally helps, but it is not always true. The quality and location of the newly added labeled samples can significantly influence the outcome. The increased data might not always improve accuracy.